Hey there, chemists. In this lesson, we are going to look at carbohydrates and look at how we represent simple sugar molecules, like the glucose molecule, in different ways. This is a very short introduction to some of the things that you'll see in biochemistry, which is really the chemistry of all the biomolecules and how we make building blocks from things that we consume, things like fats and oils, proteins, and carbohydrates, which break down into fatty acids, amino acids, and sugar molecules. But today we're just going to pan down and look at carbohydrates very specifically and how we draw them in different ways, because there's many ways to represent them. First of all, a carbohydrate is anything that has the molecular formula pattern CnH2ON. So everyone should be familiar with glucose, which is C6H12O6, and it does fit that formula. Now many, as you know, different chemical compounds can have that chemical formula. The isomer known as glucose happens to look like this. If we were to draw it in a simple line structure that might be familiar to us, it's a 6-carbon chain, and it has an oxygen on every single carbon. And I'm going to draw it the way that we're pretty familiar with drawing line structures in this course. And you can see when I draw it in that fashion, all the asymmetric carbons that are there. We could even, for fun, give it a systematic name if we wanted to. This is a 6-carbon aldehyde, so this is a hexanal, and it has 5 hydroxys on it, so this is a pentahydroxyhexanal. Those alcohols, those hydroxys, are on carbons 2, 3, 4, 5, and 6. So this would be a 2, 3, 4, 5, 6 pentahydroxyhexanal, and then it'd have to specify R and S for every single one of those stereocenters. So if you want to, you can jot down, this would actually be called, parentheses, 2R, 3S, 4R, 5R, 2, 3, 4, 5, 6, pentahydroxy hexanal. Now, no one really calls it that. This is the glucose molecule, so we're going to call it glucose as well. And what I want to do is show you a couple of different ways that we can represent this. First, I want you to imagine you have a model of that in front of you, and I'm going to rotate around a couple of the carbon-carbon single bonds and just draw it a little differently. And then we'll see how we turn this into a different flat representation called a Fischer projection. Imagine you had that molecule in front of you from a model kit, and we drew it so that it fit a carbon backbone like that. I'm stretching it out quite a bit, where the aldehyde is over there, abbreviated as a CHO, and the CH2OH is over there on the right-hand side. And I'm going to fill in those 4 asymmetric carbons, actually from left to right, one at a time, but each one has direction, with a group coming out of the plane and a group going into the plane. And each one is an H and an OH. And if I imagine taking this representation of it and turning it into this molecule, what I would see that I have is, on that first carbon away from the aldehyde, I have an OH going into the plane and an H coming out. And then I actually have the opposite on the next one, an OH coming toward you and an H going into the page. And then it goes back the other way once again, H coming out of the page, OH going in, and then that repeats, H coming out, and OH going in. Now, if I imagine that I'm sort of floating above this molecule and looking at it along that carbon skeleton, that 6-carbon chain is a vertical line right in front of me. And these groups that are coming out of the plane and going into the plane in this representation are actually all just sort of coming toward me from that long vertical chain. And then you get to what we call a Fischer projection. So a Fischer projection is where you represent this 6-carbon chain as a single vertical line. We put the aldehyde at the top, we put the CH2 at the bottom, and those 4 asymmetric carbons are represented by these 4 intersections of lines that are just drawn as single solid lines without bold or wedged notations, but they communicate direction. This was developed by Emil Fischer in the late 1800s, and it's still used today just as a simpler way of drawing carbohydrate and sugar molecules to represent direction on a 2-dimensional piece of paper. What we have, if I go back to the representation I was just looking at, I have an OH going away from me on that carbon, and that carbon, And if again I'm sort of like floating above this structure looking at it that way, those are actually all on my right hand side, aren't they? So it's right there, and then there, and then there. And this other one that's coming out of the page in this first representation is conversely on my left. And then I have H's occupying all the other sites. That is glucose, and that is a Fischer representation, F-I-S-C-H-E-R, Fischer projection. And we can use these for other drawings that are not carbohydrates. In the lower right, there's a little box that sort of shows how a Fischer projection works, where if you're looking at any molecule with an asymmetric carbon, we think about it as if those two groups that are horizontally drawn are coming out of the page toward you. So this is a correct representation of a molecule, but it communicates the stereochemistry that we would see in a three-dimensional molecule with an asymmetric carbon. Since I have your attention of this little box here, let me show you some allowed redrawings and some not allowed redrawings. First of all, it's not okay to redraw it just rotating at 90 degrees. That would completely invert the stereochemistry. In other words, if I just rotate every group by one 90-degree direction, I'll redraw what I'm talking about. In this case with C at the top, A on the right, D on the bottom, and B on the left. Those are not the same thing. I actually inverted the stereochemistry by rotating it. I can rotate it 180 degrees. That's okay. I could put A on the bottom, D on the left, B at the top, and C on the right. That's the same thing. I didn't invert stereochemistry. You can also do a partial rotation, I'll call it, where you lock one group and rotate the other three. And this works no matter which three you pick. So I'm going to lock the one at the top, the B, and rotate the other three so that C is at the bottom, A is on the left, and D is on the right. That still has the same asymmetry as the original one. If you can't see that, you can make a different drawing of it and prove to yourself that that's indeed true. So let's get back to how we redraw this. This is called the Fischer projection, and this is actually the same molecule as what we looked at a moment ago. That's a chair conformation of a glucose. How is one cyclic and one acyclical? They interconvert. This is called a pyranose form of the glucose molecule, and it's favored when it's a solid. And the open chain form with the aldehyde group exposed is more present in solution, but they exist as an equilibrium mixture. You can interconvert them, and I'm going to show that in part as we turn one drawing into the other. The first thing I'm going to do, actually I'll highlight those OHs. I mentioned those three OHs down there. They correspond to that, and that on the right-hand side, and that on the left in those respective colors. Now let me rotate a little bit of this molecule by just doing one of those Fischer rotations, I'll call it, because if I want to get this to draw into a six-membered ring, and the six-membered ring has to have an oxygen in it. So where is this oxygen in my open chain form? Well, a better question is, where is this carbon, this frankly most interesting carbon right here? That is a hemiacetal. Remember, a hemiacetal is a carbon with an OH attached and attached to the same carbon in OR group. It's sort of halfway to an acetal. We saw that back in our acetals unit a few weeks back. And it's the hemiacetal carbon that used to be the aldehyde. So formerly aldehyde, formerly CHO. So if that used to be my aldehyde carbon, that oxygen has to be atom number 6 when I count along the chain. So let's do that. This is carbon number 1, the CHO, then I get to 2, 3, 4, 5, and I have to go over to that oxygen to get to number 6. That will give me a six-membered ring. And to make this easier to figure out what happens to the other stereocenters, I'm actually going to do one of those rotations about just that asymmetric carbon. So I'll start with my sketch of a Fischer template. I've got 4 horizontal lines for this particular one. 1, 2, 3, and 4. The first 3 are the same. I have an OH on the right, an OH on the left, and an OH on the right, and then the other spots of those horizontals are taken up by hydrogens. Now the last one I'm going to rotate. I'm not changing the configuration, I'm just doing a rotation of those 3 groups, and I'm keeping this entire 4th group the same. That's an allowed rotation. So this OH will be at the bottom. So OH at the bottom. This CH2OH will now be on the left. CH2OH. And then this H will be over here on the right. That's the same molecule. I did not accidentally invert any stereochemistry. And the reason I did that is because I want to draw the 6 atoms that become the ring all in one line. This is just my way of doing it. 1, 2, 3, 4, 5, and 6. That's if you want to make a 6-membered ring. It should be noted that glucose and other sugar molecules can make other ring sizes, most commonly 5, in addition to the 6-membered ring that we've seen probably more than any other. Those are called furanoses instead of pyranoses, so that I would get to a different oxygen atom, namely that one, to make a 5-membered ring. But anyway, let's get to the 6 and we'll go from there. So where do I go from here? I'm actually going to make the entire molecule fall on its side and draw it no longer in a Fischer, but pretending I'm just looking at it from 90 degrees. And if I do that with the OH on the left-hand side and the CHO all the way on the right, I still have 1, 2, 3, 4 now vertical lines. This is sort of a fake Fischer. What used to be on the right-hand side is now on the bottom. So I have an OH right to left, H, OH, and H, and then on the top is what used to be on the left, right to left, I have H, OH, H, and then CH2OH. And then this is where it cyclizes. It will cyclize to give me a hemiacetal. That's how you get the ring. That oxygen will form a bond with that carbon of the aldehyde. Remember, that's what happens when we have an alcohol and an aldehyde. There's a very simple example in intermolecular. The alcohol can attack the aldehyde, the electrons go up, and you get a new hemiacetal. You're on your way to a hemiacetal. And when this cyclizes, I'm going to draw it in the 6-membered ring with the oxygen in the ring, but I'm going to draw it as a flat hexagon and then work my way around the ring. This oxygen is now this oxygen in the ring. This carbon, I'll make this carbon right here. What does that carbon now become? It becomes an OH bond, and it actually isn't specified in either direction. Both are possible because when an alcohol sees an aldehyde, we can attack that aldehyde from either side of the face of the aldehyde in this particular case, and you'll get both, and we actually have designations for both. So what about the rest? What's, working my way around the ring? What's this carbon right here? Well, that's this carbon right there with a CH2OH pointing straight up. So I'm going to draw it straight up. And then I work my way around the ring as I work my way down the carbon chain. So if this is that group, I now have an OH pointing down. And then I get to an OH pointing up. And then I get to, lastly, an OH pointing down. This is called a Haworth projection. And it's so close to the chairs that we're used to seeing. It just doesn't specify axial and equatorial, but it still shows the same relative direction, let's call them up and down, for all those asymmetric OH groups attached to the different positions. We can do one more redrawing of this and actually turn it into a chair, and that's going to make me mimic what we already saw in the very beginning up at the top of your notes. There's a chair. So working my way around the ring, this CH2OH, I'll make that carbon right there. It's up at that carbon is equatorial. Then the next one is a down OH, down at that position is also equatorial. The next OH is up at that position is equatorial. The next one is down at that position is equatorial. And then the last one I'm going to draw as a squiggle because both are possible. This is called the pyranose form, because it's a 6-membered ring. That's from the molecule known as pyran, which is a 6-membered ring with an oxygen flanked by double bonds, hence the pyranose form of the sugar. There is another version of this called a furanose form, and that's named after the furan molecule, which is actually an aromatic molecule. We saw this back in the benzene unit. Looks like that, so there are such things as furanose forms. So, in the solid state, the closed chain form is usually what we see for sugar molecules like glucose, and then in aqueous media you see the open chain form, but they interconvert. these are different isomers of the same molecule. They have the same same molecular formula, so they are just sort of like constitutional isomers, but they're very related, so we talk about them in the same context. I'll just wrap this up by showing you the two different diastereomers that we would actually specify, because that squiggle line should bother a lot of you. Like, what's going on with that? Well, it's just to indicate that both are possible, and I'll show you both of them and tell you how we describe them. And it's easy to remember glucose. This is a good time to point out that glucose has an easy chair to memorize. If you draw it this way every time, just remind yourself that every asymmetric carbon is axial, and you have two possibilities for that hemiacetal carbon, the one that used to be the aldehyde. But all the other positions are equatorial. So it's easy to just sort of memorize glucose if you want. The ones that are different or the one that is different is that position right there. The OH could be up equatorial on the left or down equatorial on the right, and they are interconvertible. These are called two different anomers of glucose. The one on the left we call the beta anomer, and the one on the right is called the alpha. And one way to remember that is the relationship between the CH2OH group back there and the OH in question on what they call the anomeric carbon. In the alpha, they are anti to each other, as opposed to them being syn to each other, and that's what it actually refers to, the relative direction in the chair between that OH group and that CH2OH group back there. But you should have no problem recognizing that these are just diastereomers of each other, aren't they? But they're a very special class of diastereomers because they can interconvert so easily. So, with that in mind, let's take a look at just one practice problem that's not glucose, but it asks us to do the same thing. And here I'll reiterate, it's a good idea to just memorize the structure of glucose, and everything else can be thought of as relative to that, at least for the 6 carbon sugars, which you'll probably see more of than the other carbon chains. So glucose, as I said, is the chair with everything equatorial. In the open chain form from the aldehyde down, I honestly just memorize right, left, right, right. That's the order of those OH groups. So if we are asked to draw a pyranose version of a molecule like this, first I just compare it with glucose. It's a 6 carbon chain. I draw a skeletal chair. And I'll fill it in as if it is glucose first. Just remind myself what glucose looks like. Everything is equatorial. That anomeric carbon that used to be the aldehyde, I'll make a squiggle. This is glucose. I gotta find what's different about this compared to glucose. Well, glucose is right, left, right, right. Aha, this one is different. That's the one that's flipped. So which carbon is that? If I number the aldehyde 1, 2, 3, 4, 5, 6, it's carbon 3. And remember, the aldehyde carbon is the one that becomes the hemiacetal. So this is carbon 1, 2, 3, 4, 5, 6 in the chain. So it's carbon 3 that's inverted. So that just means I need to change that up equatorial OH to a down axial. And then I don't have to go through all that drawing that we did on the front. That was really just to show you where it comes from. But obviously, to save time, you can think about just what it is relevant with respect to other molecules. Okay, that's just a quick introduction to carbohydrate molecules and how we draw them with different projections.